Hello everyone, welcome back to another video on linear algebra. I haven't made a video in a while, and that's because I am also a student. I'm a chemical engineer major, and I'm a senior, so things are getting pretty intense right now. But I'm glad I got to make some videos while I had some off time. So today we're going to be talking about the properties of determinants, and we're also going to include some Kramer's rule. So let's get into it and start discussing some of the properties. So we have this first property, and it's going to be the determinant of Ka, Kb, Kc, Kd. And from the previous video, we actually had a similar case where we basically factored out this K, and it comes out of the first top row, and then if we actually factor out another K from the bottom row, we get K squared, the determinant of A, B, C, D. Okay, so the next one, number 2, we have the determinant of K times this n by n. So if we were to pull out this K, we'd actually have to pull out, we'd also have to include this n, and that n is, it's actually, so whatever this n by n is, that n has to correspond to that value. So if this was a 3 by 3, that n would equal 3. Okay, so that's not too bad. And sorry if you hear some munching, it's actually my dog. He's having a nice lunch. Okay. So moving on to the third one, we have if A is an n by n matrix, then A is invertible if and only if the determinant of A does not equal 0. So then that means that A inverse is equal to 1 over the determinant of A plus, multiplied by whatever we have in that those brackets. Okay, so moving on to the fourth one is the determinant of AB could actually be separated in the form delta A, the determinant of A multiplied by the determinant of B. So the fifth one, moving on, we have the determinant of A inverse is actually going to equal 1 over the determinant of A. Okay, not too bad. And the sixth property we have, the determinant of A is equal to the determinant of A transpose. And we'll get into some examples. But before we do that, we will go ahead and prove the fifth property. Oops, okay. So if we're saying that A is invertible, that means that an A inverse exists. So if A is invertible, this implies that A inverse exists. Okay. Also, let's remember that the determinant of the I matrix, the identity matrix, is equal to 1. Okay, so if we have A times A inverse, that equals the identity matrix. And if we take the determinant of both sides, we have A times A inverse is equal to the determinant of the I matrix. Okay, so now we're going to apply the fourth property here. And we're going to say that the determinant of A multiplied by the determinant of A inverse is equal to 1. Because again, the determinant of the identity matrix is equal to 1. Okay, so let's just move this guy up here. And we can go ahead and divide by determinant of A to both sides. And we'll be left with the determinant of A inverse is equal to 1 over the determinant of A. So we divided by the determinant of A to both sides, and that cancels out that. Okay, so that is verified. Alrighty, so moving on, we have this problem. So we need to verify that the determinant of Ka is equal to k to the power of n times the determinant of A, given the matrix A and the k equal to -4. Okay, so let's pick orange. Okay, so let's start off by saying the determinant of -4a equals, let's just, since we don't know if it's equal to, let's just like question if it's equal to. So part of our properties before, we were able to remove the k to the n, if you recall. So that's going to be -4 to the power of, well, this is a n by n matrix, and this is a 2 by 2 matrix. So that n is going to equal 2. So we have -4 to the second power, multiplied by the determinant of A. Okay, that sort of simplifies a few things. So let's go ahead and write this out. Let's write this out completely. So we have, actually before we talk about this one, let's prove this left side. Let's expand the left side. Alright, so we'll start with the left side. So here we have the determinant of A. So we have 2, 2, 5, and -2. Okay. And then if we apply that -4 to all the components, then we have the matrix of -8, -8, -20, 8. Okay? So that's the left side. Now let's find the determinant of -8, -8, -20, and 8. So when we complete that, we get -64 minus 160, and that's going to equal -224. Alright, so there's that. Okay, I'm going to switch colors just for your viewing pleasure. I'll mix it up and do purple. Okay, so now for the right side, we have -4 squared. That's a 2. Determinant of A. And that's going to be 16 times the determinant of 2, 2, 5, -2. Okay, so we get 16 times -4 minus 10. That's going to equal -224. Okay, so we have verified that this is indeed equal. Okay, because -224 is equal to -224. And if it wasn't, I would have discovered something so tremendous that I would need a Nobel Peace Prize. Alright, so moving on, we need to use the determinant to decide whether the matrix is invertible. Okay? No problem, we could do that. So given this matrix A, we will find the determinant of A, which is actually I'm getting ahead of myself. So in order for something to be invertible, remember that the determinant A cannot equal 0, and that would prove that A is invertible. Okay, so let's start by taking the A matrix and performing some operations on it to make it more manageable. So we have 2, 0, negative 2, 0, 3, 0, 3, 2, 4. Alright, so the first operation that we could do is we could basically remove this, negative 2. And again, I like to focus on one row and trying to make those zeros instead of like being sort of confused on where you start. I start on the first rows. I'm sorry, the first columns. I misspoke. Start on the first columns and then move over and do each one. Okay, so I would say R1 plus R2 is going to R3 is going to equal our new R3. Because I could see that can cancel out. Okay, so once we do those operations, we get 2, 0, 0, 0, 3, 0, 3, 2, negative 1. I did make a mistake on the initial one. This is a negative 4. Okay. Okay, so if you notice here, we have a triangle of zeros here. So that means what we could do is take this diagonal and basically multiply it. So then we have 2 times 3 times negative 1, which is negative 6. And since the determinant of A does not equal 0, because it equals 6, negative 6, that means that A is invertible. So we did that. Okay, so now moving on to Cramer's rule. So Cramer's rule is just an explicit formula for to find the solutions of a system of linear equations. And you'll see that there are many equations, and there's going to be many unknowns. So it's just a quicker way to solve for the unknowns. Alright, so we're going to take these equations and we're going to solve it using the Cramer's rule. Alrighty, so first we're going to put this all into one matrix, and that's 1, 2, 4, negative 3, negative 1, 0, 1, 0, negative 3. Okay, so remember the sign convention that we're going to have here, plus, minus, plus, minus, plus, plus, minus. Okay, so remember that sign convention. Alrighty. Get the white. Okay, so now we're just going to find the determinant of that. So that means we have the 1. We're going to start with the this first row here as our basis. We have the 1, -1, 0, 0, -3, plus 3, since it's a minus and a minus. 2, 0, 4, -3, and running out of room, plus 1, 2, -1, 4, 0. Okay, so we'll go ahead and solve that, and we get that it's equal to 3, since that's 3, yep, 3 minus 18 minus 4. Oh, this is actually a plus, since that's minus 4, and then that's a minus. Okay, yeah, there you go. And then we get -11 is equal to this capital D. And then we're going to find this dx1, and the dx1 is basically my notation. So what we're going to do is include our constants. So here we have the 4, -2, and 0. We're going to include those into our matrix by replacing each row. So for this instance, we'll do it 1, 2, 3 times. Okay, I'll show you what I mean by that. So we're going to replace the first column with the sorry, that's a positive 4. 4, -2, and 0. And then -3, -1, 0. 1, 0, -3. Okay. Now we're going to look at this matrix, and I typically look for the most zeros in a row and then use that as my basis in terms of which variables I want to be multiplying, basically. So the one with the most zeros is great because then that makes it a whole lot easier. So if I take this bottom row, this 0 in this bottom row, we'll start off with that 0. So basically, if I multiply every term here by 0, it's going to be a 0. So I'm just going to start here, -3. So I have -3, smaller matrix for -3, -2, this one. Okay, so then I get -3, and it's -4 plus 6. Oh, I'm sorry, minus. And that's going to equal -10. And then we have -10 times -3, which is going to be 30. And we're going to do that same substitution for each column. So dx2 is going to equal 1, 2, 4, 4 minus 2, 0, 1, 0, -3. Okay? And then if you were to compute that, you're going to get 38. And if we do the same with dx3, you'll get 1, 2, 4, and that is my dog snoring, minus 3, minus 1, 0, and then we'll substitute the constants here for negative 2, 0. And this is going to equal 40. Okay, so you gotta trust me on that. Okay, so now we have x1. Try another color. Okay, so x1, which is our variable x1, is equal to dx1 over the main d. So that's going to equal, where are we at? 30 over negative 11. Negative 11. So x1 is equal to negative 30 over 11. So we solved our first variable. Excellent. So happy, so easy. Okay, so same thing with x2. x2 is equal to dx2 over d. And you get 38 over 11. Perfect. So now x3, same thing, dx3 over d is going to equal 40, that was ugly, over negative 11. And that's a negative. Equals x3. And that is how you do the Kramer's rule to figure out your unknown variables. So moving on, we have this problem. If the determinant of A is equal to negative 2, and the determinant of A is a 4x4 matrix, what does the determinant of negative A equal? Well, if we think back to our properties, this is actually not so bad. So let's say that the determinant of negative A equals, so yeah, we don't know yet. So if you remember, we pulled out a constant, or k, before, but now we're going to pull out the negative 1, because there is a negative 1 there. Oh, this looks terrible. Okay. And that's the determinant of A now. Okay. However, we're missing something. Oh, you must have known. Probably caught that. This n. What was that n equal to? Oh, that's right. It was equal to the n by n matrix. So it's 4. So that is 4. Uh-oh. What is negative 1 to the 4th power? Oh, that's right. It's just 1. Okay, so no problem. The determinant of A, what does that equal? Oh yeah, negative 2. So here we have the determinant of negative A is equal to negative 2. There's your answer, buddy. Okay, let's see this next one. So let's separate that. Determinant of 2A inverse. So if the determinant of A is a 3 by 3, and that 3 by 3 is equal to 7, what does the determinant of 2A inverse equal? Well, again, we are going to pull out that 2, and then we'll need our n variable, the determinant of A inverse. Okay, so what is our n? Oh, okay, that's right. No problem, it's 3. So now you have 2 to the 3rd power, determinant of A minus 1. A inverse. Okay, so here we have the determinant of A is equal to 7. If you remember, back to our properties, the determinant of A inverse was equal to 1 over the determinant of A, which means it's the determinant of A inverse is equal to 1 over 7 in this case. So 2 to the third is 8 times the determinant of A inverse. Here is 1/7. So 1/7. And that's going to equal 8/7. So the determinant of 2A inverse is 8/7. So that's a good one. You might get that on your exams. But if I was a professor, I would give this tricky question. What is the determinant of 2A, 2 times A inverse? And let's see. So the determinant of A is still at 3 by 3, and that determinant of A is equal to positive 7. Oh my goodness, what does this equal? Oh, I'm freaking out. Just kidding. Let's take this step by step, okay? What if we could just, I don't know, say turn this into just... What if we just imagine that it's an A, right? This whole thing. This whole term is the A. What does that look like to you? Oh, the determinant of A inverse? Okay, so using our properties, doesn't that just equal 1 over the determinant of 2A? Right? Because the determinant of, go back, the determinant of A inverse is equal to 1 over the determinant of that A matrix. Okay, yeah, that's no problem. We have the same thing here. So we basically have the same thing here that we did before. Now we don't know the determinant of 2A, but what we do know is the determinant of A. So we would have to pull out that constant. So how do we pull it out? We pull out that K to the N, and the N in this case is 3 still. Determinant of A. Awesome. So what is the determinant of A? Oh yeah, that's the determinant of A is 7. However, keep in mind this is 1 over 8, 1 over delta A. So we have 1 over 8, and then 1 over 7, which is just 1 over 56. Alrighty. So I think that will conclude this chapter, or I'm sorry, this lesson. And I think, yeah, we'll move on to the third chapter, which will be a new vector space. We'll be dealing with Euclidean vector spaces, and we'll just start introducing vectors in the next video. So if you have any questions on this video, you can go ahead and ask them in the comments down below. If this did help you, go ahead and give this video a like. But possibly, if you want, you could click the subscribe button and turn on that bell notification to get notifications when I post again. All right, so I hope you enjoyed it, and I hope you're doing well in school.